Hello everyone, welcome to our live webinar. My name is Lisa and I'm from the Transvalor marketing team. So let me introduce our speakers today. Nadine is our marketing product manager and Max was supposed to be with us today, but unfortunately he can't make it. So Patrice, our engineering expert, will replace him. It's an honor to have him as a speaker today. We're very lucky. It's not every day. So today's webinar is about heat treatment and how Transvalor solution can help to predict and improve final properties of heated components. We will exhibit the benefits of SIMHEAT applied to both thermal and thermochemical processes. After this presentation, we will meet again for the questions and answer session. So feel free to type your question in the question box. We will show you everything later on. I will turn the camera off and give the floor to my colleague Nadine.
Okay, thank you, Lisa. Then, hi everyone. Today our webinar is dedicated to how can simulation help to predict and improve the final properties of the heated components. Before we start, just a few words about the GoToWebinar platform and how to operate. Thanks to the, you can use the orange arrow here to minimize the control panel, okay? Your microphone will be turned off during the whole webinar. Then if you have any question, please feel free to type your question in the dedicated area. At the end of this webinar, we will come back to you and we will answer all your questions. If we don't have time to answer all the questions, we will send you an email with the answer. This is the agenda of this webinar. First, we will start by a review about our company, who is Transvalor, how we can help you. Then we will see the SIMHEAT global scope. After, we will see SIMHEAT application on several domains, from quenching to night threading to induction. And at the end, we will finish with the conclusions and the novelties, which will arrive with the new version of SIMHEAT and Forge NXT 4.0. Let's start with the company and how our solutions can help you in your daily work and increase your productivity. Then who is Transvalor? Transvalor is an independent software editor providing leading-edge solution for virtual manufacturing. It has been founded in 1984. We are based in south of France in Sofia Antipolis. We supply the manufacturing industry with a process simulation software, giving keys for rational engineering decision-making. We provide added value engineering consultancy and services to help you to tackle the new technical challenges. Then if you have any project and you are working on it, you don't have the solution, please do not hesitate to send us your project, and our customer service and our service department will help you to respond and to overcome this challenge. We work in very close partnership with SIMHEAT Mine Polytech Research Laboratory, where there is more than 120 scientists that they are working continuously to integrate the research work and like this our software becomes innovative. More than 1,000 customers around the world entrust our solutions. Like I said, we are based in the south of France. It's a quite nice region. And as well, we recently opened new subsidiaries in United Arab Emirates and as well in India and China. And we have different distributors all around the world. We work in close partnership with our clients to help them to increase their productivity. For this reason, we opened recently these new subsidiaries to be near our clients. Then, like I said, more than 1,000 companies worldwide entrust Transvalor with their material forming simulation needs. These companies are working in different sectors, for example, in energy, in aerospace, of course, in automotive, in heavy industry, and several academics as well are working with our solution, and they are working to give us more innovative research to integrate them constantly in our products. Here now we will see how our solutions can help you. Then for the person who don't know Transvalor, we have a big platform that help you for modeling the whole manufacturing process from the casting. Here, for example, we see the casting. And here we see an example of casting to the forging. Here we can see an example of a crankshaft forging. Okay, and we see how the metal flow in it. To the heat treatment simulation, now we see the induction heating of a billet. To the welding, then we can see the welding. And at the end, to the fatigue computation and life cycle management. We can see how the crack go in the part. We can as well analyze the microstructure evolution during the wall forming process from the casting to the forging till the fatigue. And as well, it is possible, like we see here in this video, it is possible to analyze the evolution of the microstructure at the micro scale. Let's talk about SIMHEAT global scope. Then let's talk about the globe of what is the global scope and of our heat treatment solutions, how our solutions can help you. Today, several heat treatment operations can be modeled. You can model the whole heat treatment cycle from the example from induction to quenching till carburizing. Then it is thanks to the modeling to the heat treatment cycle. You will predict the mechanical properties of your part accurately. Thanks to the heat, it is during the heat treatment simulation that that the part will get its mechanical property. As well, it is possible to make surface treatment, for example, to model carburizing or even to model nitriding or carbonitriding. During these simulations, you can predict several scalars. For example, you can predict the temperature evolution, the phase transformation, how much ferrite benite do you have in your part, what is the microstructure of your part. You can evaluate the hardness, the residual stress, the yield stress. You can predict the distortion after, for example, after a quenching or during heat treatment. You can determine the plastic strain. And for sure, for surface treatment simulation, you can see the carbon and nitrogen concentration evolution. Like you see with our solution, you can model the whole heat treatment cycle. You can play on several, for example, parameters. We can see the influence of the isothermal holding. We can see if you have a question about which temperature to use and during your heating, you can determine it. We can see the influence of several quenchants that are integrated in our database. Like you know, in our database, we have a rich material database that it's rich in steel, aluminium, and titanium alloys. As well, it is possible to use directly your experimental data, for example, to use your experimental curve, your CCT curve. It is possible, we have a TTT diagram generator that will help you to generate your TTT diagram file. Our material file is our software is compatible with GMAT Pro material files. Then it is possible to use directly GMAT Pro files in our solutions. We have a rich quenchant database thanks to our collaboration with Quaker Houghton. It has been some years that we are working in this collaboration with Quaker Houghton. Thanks to this collaboration, we enrich the quenchant database and our software to be the more realistic as possible. We have several dedicated templates that allow you easily to model the heat treatment cycle. For sure, we have several tutorials to help you to use easily the software. Now, let's see together some SIMHEAT applications, how, thanks to our solution, we can respond to the customer need. First, we will start with a simulation of heating and quenching. Then for a long time, heat treatment was considered as a black box. We know what goes into the furnace and what comes out, but we don't know what happened inside the furnace, for example. For this reason, the simulation can be very useful. You can, thanks to the simulation, determine at which time the part is full austenite, for example, and then you stop heating the part. So thanks to the simulation, you can reduce your CO2 production. Here, for example, we see a heating of this shell quenching. So of this shell. This this example has been done with collaboration with Framatome. Here we see the temperature of the part that will increases. And we can see here the apparition, then how the perlite and the ferrite phase will be transformed into austenite. And we can see how after heating, the part will be full austenite. After modeling the heating operation, now we will focus on the quenching operation. The shell is quenched in a water bath at 20 degrees Celsius. It will be quenched for approximately 1 hour. As you know, the heat transfer coefficient depends on several parameters. For example, the bath agitation, the bath kind, is it water, is it oil, the temperature, the orientation of the part, is it vertical, is it horizontal. Here, for example, in this case, to take into account what happens inside the fluid or the boiling of the fluid, we will consider a heat transfer coefficient that is function of the surface temperature of the metal. Then it is not a constant heat transfer coefficient. This is more accurate to consider a heat transfer coefficient having the following curve. Then we can see that the heat transfer coefficient then varies with the surface temperature. As well, to model the quenching and then the cooling in the air that happens before going on the water, we can model the heat transfer coefficient using a switch function. Then we can see here that when we are on the air, we have a small heat transfer coefficient. Then we have an important heat transfer coefficient when we go inside the water. Please note that the heat transfer coefficient can vary with different it can be a function of x axis or y axis, then it depends. Here, for example, we take it function of z axis. It can be function of the time as well. By using these parameters, we see here how the temperature will decreases when we are in the water tank. And here we see the martensite evolution. We see the apparition of the martensite on a small surface of the shell. Like I said before, thanks to our collaboration that we are working on with Quaker Outen, thanks to this partner with Quaker Outen, and we enrich our material, our quotient database with several quotients. Here, for example, we see several quotients that solutions that comes from Quaker Outen that we integrate in our software. The ACR solution, the oil, the PAG solution, PVP solution. Then we have the aim of this integration is once you use in reality a Quaker Outen quotient with the software, you will find directly, you will go and select your quotient. Then your heat transfer coefficient will correspond to what you have in reality, and your simulation will be accurate. Now, if none of the quenchant correspond to your quenching conditions, it is possible to calculate the heat transfer coefficient using the optimization model. How to do it? You will define a heat transfer coefficient function of the temperature, and then you will use the optimization model and you will make a reverse analysis where you will, by making a reverse analysis, you will determine the heat transfer coefficient that fits well with the temperature measured in the thermocouple. Then you will fix some thermocouples in your part, and then you will use the optimization model to determine which heat transfer coefficient give you the most accurate results and the most near results to the one measured by the experimental. Here we see a comparison between the experimental and the computed temperature of the best individual in this case. Then the optimization model is a very powerful model that will be integrated in the new interface NXT from the next release. You can take benefit of this optimization model to determine the heat transfer coefficient that correspond to your quenching condition, and you will be the most realistic possible, and you will have results as reality. Vertical spray quenching. Then now we will talk about vertical spray quenching, and during then this case has been then thanks to offer from Jiva Group. Thank you. This case has been done with collaboration with offer from Jiva Group. Here we have sort of a vertical spray quenching. We know that during spray quenching the heat transfer coefficient varies with the spray angle, the distance to the surface of the spray and the pot, the relative angle between the spray and the surface, and the spray water flow. Here, for example, we see the heat transfer coefficient. We can see that it is here for sure we have the sprays that are cooling this part. The part is rotating to have a uniform, a homogeneous cooling. Here we define a sensor to measure the temperature on the surface of the pot. We can see the temperature, how the temperature decreases during quenching. And here we can see the phases. We can see then the apparition of the benite on the core of the part, of the large shaft. And we see the apparition of the merton site on the surface of these two zones of the shafts. Then, like we see together, thanks to the numerical simulation, you can determine the phase transformation due to spray quenching. Here we can as well determine the distortion. Here we see the residual stress. We magnified the deflection by tens to see the distortion. Then thanks to this result, we can see the distortion of the part during the spray quenching. This is quite impressive. This is a good. Then we can see how the part moves, or then the distortion of the part due to the spray quenching. Now let's talk about surface treatment, surface heat treatment, about carburizing and nitriding. Here we present different possible treatments that you can apply on your parts. Function of this treatment, the hardness will, in the case depth, will be different. For example, during nitriding, we can see that the hardness is important in a small depth, case depth. During carburizing and hardening, the hardness is important, is very important in a big depth of the part. And during volume hardening, it is the heating in the furnace that we see before. The hardness is approximately constant in the depth of the part. Now we will focus on the carburizing and induction hardening, and we will see, thanks to these two treatments, how then the hardness distribution and what is the influence of these two surface treatment on the steels. Here we have a carburizing case where on the surface of the part, we enrich the surface of the part by 80% by the carbon. Here we see the carbon distribution and the depth of the part. Using this type of simulation, you need a refined mesh on the surface of the part. Here, the mesh has been refined on the surface of the part to see the gradient of the temperature, and because this is in this specific surface of the part where this is where there is phase transformation. During carburizing, here we have the initial CCT diagram that the part had before carburizing. And once the part is carbon distribution change after carburizing, it is possible the diagram CCT diagram will be shifted according to the carbon rate, as we see here in this diagram. Then here we see the new CCT diagram that we obtain after carburizing. Then you can use this CCT diagram in the new simulation to model the whole, for example, heat treatment cycle. For example, after carburizing, if you want to model a quenching. Now we will see the results that are then after carburizing, we make a quenching, and now we are analyzing the final part, the part properties, the final part properties. Here we see the hardness. We can check here that the hardness is very. We have a high hardness of 500. 500 Vickers on the surface of the part. The core of the part is keeping ductile. And here we can see the pressure. In fact, the high on the red zone of the pressure, then high pressure indicates zones that are in a high compressive state. We can see at the inside of the part we have attraction. Then we have a high tensile state. Negative values of the pressure indicate the zone where there is high tensile state. Now we will see different results of obtained after hardening. First, we will see here the martensite distribution after hardening. Here we can see the benite distribution. Then we can see that the surface of the part is made of martensite. Inside, there is a mix between benite and ferrite, and there is no perlite. Now let's talk about another subject, the nitriding. The mechanical properties of the nitrided part are induced by the diffusion of the carbon and the nitrogen, as well as the precipitate. The total concentration corresponds to the sum of elements that will diffuse in the matrix with the elements that are trapped in the precipitates. In fact, in our calculation, we use a material file. We use the equilibrium we make the equilibrium calculation with thermocalc or even with GMAT Pro. Like this, we can obtain the percentage of each phase function of the carbon and the nitrogen. Here we can see the influence and of the mesh. Then the influence and the refinement of the mesh on the nitriding simulation. For example, this mesh is not appropriate for making nitriding, not even carburizing simulation, because it's not enough refined on the surface to capture what happened on the surface of the part. This mesh has been obtained by defining an isotropic mesh on the surface of the part. Then we define a mesh box where we fix a small mesh size inside the part, and we keep the core of the part. We have a coarser mesh inside the part. Here we use an isotropic mesh to refine the contour of the part. And we can see here that and during this anisotropic mesh, the mesh has been elongated on a specific direction. These both meshes has the same accuracy. We have the same mesh size and the gradient and the direction of the gradient of the nitrogen or the carbon. Thanks to the anisotropic mesh, by comparing these two meshes, here we can see that we have 1.5 million nodes. Then here we have 2,000 nodes. The computation time will be lesser by anisotropic mesh with having the same accuracy. Let's check the results and make a comparison between isotropic mesh and anisotropic mesh. Here, like I said, then we have a comparison between results obtained by isotropic mesh and the one with anisotropic mesh. Computation time was 20 hours for isotropic mesh and 23 minutes, only 23 minutes for anisotropic mesh. Here we see the carbon rate distribution for both meshes. And here we see the nitrogen distribution. We can check that the results are similar. But thanks to the anisotropic mesh, it is 54 times faster. Now we will focus on the nitrogen distribution during nitriding. Then we can see the nitriding distribution, and here we see the carbon distribution. Then we can see the rediffusion of the carbon inside the part due to the nitriding. Now we will go to an industrial case study. This case study has been given by Faurecia Automotive Seating. This process is made on 3 stages: carburizing, then we make oil quenching, and we have air cooling to the room temperature. The aim of the study is to get a description of the carbon potential function of the time in different position. Here we see the carbon distribution in these two positions, in this corner and in this corner. We can notice here that the upper corner is richer in carbon than the lower corner. And now, thanks to the simulation, we will measure the carbon potential function of the time of the heating time in the furnace. During this case, we take benefit of the anisotropic mesh features that I showed you before. Then thanks to this anisotropic mesh, the computation time will decreases by keeping the same precision in the areas that interest us. Okay, then here we see together what happens during carburizing, and we saw that we have that Forza get good results by analyzing even if the analysis was made on 4 materials. Okay, now we will go to another example of case hardening as well made by Faurecia Automotive Seating Company. The interest in this case is to have information on the hardness on the tooth of the part, of this mechanism's part. Then we measure the hardness on 3 heights, height 1, height 2, and height 3. We compare the simulation results with the one obtained experimentally, and we can see here that for height 1 we have the same distribution for the hardness. It is very important for the client to guarantee its final mechanical property to be sure that the part will get the appropriate properties. Here we can see the hardness distribution on height 2 and at the end on height 3. Then experimental results fit very well with simulations. Now let's talk about induction surface heat treating. In fact, thanks to the numerical simulation of induction heat treatment, you can model the heat. You can predict the heated affected zone. You can predict phase and residual stresses after quenching. You can predict the distortion of the part after quenching. You can understand your generator behavior and optimize the process. Here we see the induction hardening made on a crankshaft. Here we see the distribution of martensite that was made for 2 frequencies, a high and a low frequency. And here we see the hardness distribution. then it is possible to make an analysis on the parameter of the inductor. Okay, function of this analysis, you can determine how to manipulate, how to change the parameter and which parameter to define on your inductor. This case has been done in collaboration with NT and SNL. Thank you. During this case, the objective is to create a local structure hardening around the bearing rings while still minimizing the geometry distortion and the residual stress. In fact, the bearing ring, we want to create bearing rings that that has a very good mechanical properties, and we want then to be sure to get the appropriate phase and appropriate mechanical properties for this and in a specific zone. Obtain a high hardness, or we will obtain then the aim is to obtain a high hardness on the ball raceway contact while maintaining sufficiently ductile elsewhere. In this simulation, we will take just only we will take a portion of the part for 45 degree of the part to reduce the computation time. And here we saw the mesh that has been used during electromagnetic simulation. During electromagnetic simulation, we model the inductor, the part, and the air to model the electromagnetic simulation. Here we are analyzing what happens then during induction heat treating. We see here the apparition of the Joule heat source term. We see the temperature that decreases around the ball raceway during induction heat treating. We see here the stress distribution. We see how the austenite is distributions and around the ball raceway. Now we will go to analyze the quenching. This is the results obtained after heating. Then the temperature is higher than 1150 degrees Celsius. After quenching, we have maximum a temperature of 80 degrees. This is the temperature obtained after quenching. Here we see the apparition of the martensite. Here we can see the hardness distribution. And we see in these specific areas around the ball raceway, we have a very important hardness of 750. And here we can see the distortion. The distortion is obtained by making an overlay between the original shape. Here we can see the contour of the original shape and the final shape. Then we can see directly the distortion due to the quenching. Now we will analyze the results and compare it with the experimental. Here we see, then this is the experimental result. In blue, in blue we see the lines that separate the two phases, the martensite and the other phase. We can see that the numerical results fits very well with experimental one. We find in the specific area where needed the martensite distribution and the hardness needed as well to create a bearing rings with the appropriate properties. And here to the right, we see the measurement of the stresses, and as well we can see the hardness distribution on the depth of the part inside the part. We can see that our numerical results fits very well with the experimental one. For more information, I invite you to read the following paper. Now let's talk about aluminium. Then now we will talk about quenching and artificial aging of aluminium alloys. Aluminium is a durable light material that is easy to cast or to form, and it gets its final mechanical properties through heat treatment simulation, like usual. Then now we will see first how to model quenching. Then to model quenching of aluminium alloy, we integrate a phenomenological model. Thanks to this phenomenological model, we will compute the QFA factor, then the quenching efficiency factor, computed by the following formula. If the quenching efficiency factor is equal to 1, then it means we have a fast quenching. And if it is 0 and if it decreases, we have a low quenching. To model the artificial aging of the aluminium alloy, we use a Shercliffe HB method. During this method, we can see that the final mechanical resistance is the sum of three contribution. Sigma mean, which is the contribution, comes by considering the pure aluminium. Sigma precipitate, it is the contribution of the precipitate during the artificial aging, the apparition of the precipitate. And sigma SS, it is the solid solution strength contribution. We will make the addition of three of them to determine the final mechanical resistance. Then we can see the final mechanical resistance has the same form of the precipitate contribution. It is through the coupling between the quenching and the artificial aging that this model gets its benefit. We will model the whole cycle, treatment cycle of an aluminium. Then here, as we see in this video, here we see the quenching efficiency of the aluminium obtained after making then a quenching and a aging at 180 degrees Celsius during 600 seconds. Here we see the efficiency obtained. Quenching efficiency obtained after both heat treatment. Then now today in our solution, it is possible to model a different kind of aluminium, 7010, 7175, and 6082. If you work with any other aluminium that is not integrated in our material database, thanks to our collaboration with Mondragon University, we can help you to identify the parameters needed to compute the quenching or the Shercliffe HB parameters and to model the heat treatment of your aluminium. Now we will go to the conclusions. The key benefit of our solution, it is possible to generate KKLD-based TTD diagram for low alloy steel grade. Like we see together, it is possible to model carburizing and to make an offset even of the transformation kinetic function of the carbon rate. You can model, we have distortion models that are applicable to any kind of metals, including aeronautical alloy. You can use sensors to track the material characteristic during the heat treatment. You can measure the temperature, the phase transformation, the hardness, the distortion, the residual stress, carbon and nitrogen concentration. As well, it is possible to model induction heating simulation and to determine the heated affected zone, the phase transformation, to know your generator parameters as well. At the end, I show you how to model quenching and artificial aging of aluminium alloys. Now I will talk about the novelties that will be soon available in the next release. Then we have the material viewer that will help you to create material file from scratch. It is possible to edit material properties to plot the TTT diagram of GMAT that comes from GMAT Pro. We have improved our tempering model. We have a law that predicts the oxide scale growth and spalling. As well, to be more accurate and to be like the reality, we integrate as well a heat transfer coefficient and friction that are function of this oxide scale. You will be able to better design your inductor by anticipating its deformation, because in the next release, you will be able to make thermomechanical computation even on the inductors and to consider the inductors as deformable. As well, for induction heating simulation, this simulation will be better accurate and more, and we will gain on performances. You can take benefit of the optimization model to determine the heat transfer coefficient using the optimization model. You can take benefit of the surface-to-surface radiation and the thermal computation. Then now the radiation is available in the thermal computation. Then if you have several objects, we can see the influence of the radiation from an object on another, or as well during forming simulation. We enrich our quotient database with a new quotient database that comes from Quaker Houghton quotients. Thank you, everyone.